Morning, I'm Don Savage, the NASA Public Affairs Officer for Space Science. Welcome today to the beginning of day 2 of the World's Watching the Comet Impacting Jupiter. Following a very successful first night of observing, we're here at the Goddard Space Flight Center in Maryland today, and with us we will have some panelists discuss the results of last night's observing from around the world and from the Hubble telescope. I'd like to introduce, first of all, Gene Shoemaker, who's an astronomer with Lowell Observatory and a professor with the U.S. Geological Survey. To his left, his wife, Carolyn Shoemaker, also an astronomer with the U.S. Geological Survey and the Lowell Observatory. To my immediate left, David Levy, amateur astronomer and author and co-discoverer with the Shoemakers of this comet. And to his left, we have Heidi Hamill from Massachusetts Institute of Technology with the Space Telescope Science Institute imaging team. And I'd like to start off with Gene Shoemaker.
Thanks, Don. Well, many of you know we had an absolutely incredible night last night when we knew for the first time that we were really going to see some exciting results. The first hints came in from Calar Alto, Spain, and from La Silla in Chile. Just about the time we were giving our first announcement on that, Heidi came up from the bowels of the Space Telescope Science Institute waving a picture and showing that indeed Hubble was producing fantastic images. So Heidi's going to tell you in some detail now about that a little bit later. To bring you up to date, fragments A, B, C, and D have now all hit the planet. There are observations on the first 3 of these that we'll be able to report on. D has just come down this morning, and we're not quite ready to give you any update on that. We're going to have observations on, we'll show you an observation from Cerro Tololo in Chile, the Inter-American Observatory in Chile. And we have reports that are coming up then from the NASA Infrared Telescope Facility and from the Keck Observatory on Mauna Kea in Hawaii. But first, Heidi will tell you about all the excitement that was happening at the Space Telescope Science Institute last night. Heidi?
Thank you, Gene. It was indeed very exciting. I think we were all incredibly astonished at what we saw last night. And I'm not going to waste any time. I'm going to show you that first image again. This is a 410 nanometers, that's 4,000 angstroms, blue wavelength. You can see Jupiter on the right, and what you see on the left is a blow-up of the impact site from Fragment A. This is the first feature that went into the planet, the first large fragment that went into the planet. You can see in the blue wavelength that it is very dark indeed. We're speculating at this point as to why that might be. We think that possibly what we're mostly seeing is cometary material at this point, because comets are very dark too. I expected to see a bright feature myself, so I was a little bit surprised to see this lovely black splotch on Jupiter. It looks somewhat like a streak there in the center. We're beginning to think that perhaps that's just a projection effect. We think when we do the measurements of that outer aureole, perhaps that's the word we might use, and measure the latitudes and longitudes very carefully, it appears that that larger spreading is circular, and that it only looks like that ellipse because it's down near the edge of the planet. Same for that central streak. We're not sure exactly what the size of that is. To give you a scale, that box, the blow-up box, is 2 Earth diameters. So that feature is a good fraction of the size of the Earth. We can be very glad that this comet was heading for Jupiter and not the Earth. Now, the next image that I'll show you is at a very different wavelength. This is at the red wavelength. If we could show the next image, and you see it inverts. This is a very strong methane band, near 9,000 angstroms. Methane is a molecule that absorbs photons very efficiently. And so normally Jupiter is very dark. The only place that Jupiter is bright at this wavelength is where you have particles at high altitudes. You can see the great red spot very clearly. It's a high altitude feature. It's bright. The poles are bright. Now look at the Comet site. It's bright. That is likely to mean it's a high-altitude feature. So that was very interesting to see. At all the other wavelengths, that feature was dark. I should clarify that. At all the wavelengths that Hubble was observing, the visual, the ultraviolet, and even 9,500 angstroms, it was dark. It's bright in the methane band, and it's bright in the infrared observations that we'll hear about later. Now I would like to show you one of the most exciting things that we saw last night. Absolutely knocked our socks off when we saw this. This is a Plume sequence, and you can see this is hot off the press, and we're just taking a picture of a laser copy holdup. It's a sequence from top to bottom. In the first image, the impact has not occurred. At 2018, A has gone in and sent out a fireball that extends beyond the limb of the planet. You can see a clear separation between that fireball and the terminator of Jupiter. And we think at this point that we're seeing the shadow of Jupiter on the fireball. On the third image, you can see that this fireball is spreading. The fourth image is spreading even more. And in the bottom image, it's a flat little pancake. It's absolutely amazing. I mean, there were theories about this, but we really didn't, in our heart of hearts, expect to see it in the first impact. We expected to see it at the end when we were very close to the limb. This is not particularly close to the limb. This is a massive thing. We're talking 1,000, 1,500 kilometers above the limb of Jupiter. So that's pretty astounding. We are just flabbergasted. So I also have a video of Hubble images that are taken pre-impact, and I'm showing you this so that you see the kind of detail that's on Jupiter already, and also to set you up. Because 1 week from now, we're going to give you another movie showing what Jupiter looks like after the impacts, and that will be a very interesting comparison. So if we can run this video. Reminder, this is a pre-impact video just to show you the amazing quality of the images from the Hubble Space Telescope after its refurbishment mission. This is the wide field camera. We will also be taking close-up views of the impact sites in the planetary camera, which has a factor of 2 greater resolution. And I am really looking forward to seeing those images. Thank you.
Okay, that's great, Heidi. Maybe Carolyn will tell us a little bit about the excitement that we're having last night.
All right, we have a reaction tape from the OSS that talks about the celebration. I think you know that we just all literally hit the ceiling when we heard the results. It was too exciting to believe, and it's something that we'll always remember. The reactions, I think, from all over the world show that excitement. Can we have that B-roll?
So it's on the way on the
You can see people looking eagerly here's Heidi examining the images earnestly. We all did. Every single one of them just had us breathtaking. And there's Hal Weaver looking hard. All of the team members, they're just, you can see these people have worked extremely hard to get the results. And they were all thrilled, and we're all thrilled for those.
Rita Beebe
is Heidi's still excited. I don't know whether she's more excited here or there. But we had a great time celebrating.
Melissa.
Rita hasn't moved.
she's still looking puzzled. There we go.
There's that bottle of, the infamous bottle of champagne.
There was just water in that.
Yeah.
Everyone was ready to celebrate.
Okay, that's wonderful, Carolyn. Well, David, let's hear about some of the other early reports.
Okay, yeah, Heidi, we have to work on getting you a little more enthusiastic about this. Well, I thought we would have to make stuff up, but I don't know if I'm going to say everything that I need to say. We started observing, getting observations from Calar Alto in Spain. Impact A was observed with the 3.5-meter telescope there. The plume appeared. Now, the observation of a plume is absolutely amazing. It was, as Heidi said, it was not expected for this fragment. The later ones, especially W at the end, is going to be really quite close to the limb. And to get so much from this first little impact, I'm wondering if we could take a look at that picture of the comet behind us with A over there. Look how small that is compared to what's coming later on. I mean, look at G over here. I mean, this is just the orchestra warming up. So from La Palma with the 2-meter telescope, the impact site was visible. The impact site was visible in images obtained with the 1-meter Capitan telescope from La Palma. There is a report that, if confirmed, is really interesting, of a visual sighting of the meteors from the WISE observatory. That's as flashes as the comet started to go into Jupiter's upper atmosphere and behaved as a normal meteor would on Earth. But the meteors on Earth that we see in the night sky are objects the size of a pea or a grain of sand. This is the impact of something that's at least 1 kilometer in diameter coming into Jupiter, possibly seen. The two independent observations were made with small telescopes. They report a possible sighting of a brief, sharp flash. By brief, we mean less than 1 second duration, near the limb, near the edge of Jupiter. And it was at the approximately correct location. Jim Scotty, who was at the WISE observatory at the time, has asked me to be really careful with this report. I don't want to, it needs to be mentioned because it's out on all the electronic mail, but I don't want to put a whole lot of credence into it just yet until if we get other observations of other flashes. But because there are these two reports, it means that other flashes could be visible with people using small telescopes, if this is true. And I don't know that it is. I'd like to be conservative and say it probably isn't. But it means that people with small telescopes who know exactly where to look on the limb of Jupiter at the right time do have a chance of seeing future flashes. Amateur astronomers should really, this is a red alert for amateur astronomers with small telescopes. There was an observation from the 0.4 meter, that's a 16-inch telescope in western Massachusetts. They saw a bright spot at the impact on, this is the impact site for Fragment A. The South Pole Infrared Explorer, a 60-centimeter telescope, has detected the plume from Fragment A. It's being detected all over the place. Fragment B was also detected from the Keck telescope and not detected from a number of other sites that would have expected to detect Fragment B. If you look back at that picture, though, notice that Fragment B, which is the second one there, is not exactly on the line of images, on the line of comets. There, that's a good one. B is a little bit above it, and we interpret that as being that fragment split off from the main comet after July 7th, 1992, when the main comet split apart. And if this, and the fact that Fragment C, which is right on the line, was also detected, and detected so strongly, I think we can, doing a little bit of arm waving here, suggest that the Fragment B and all of the other fragments that are off the line might be weaker. They might be more loosely held together, more of a rubble pile than A and the other fragments that split up right at the time of closest approach back in 1992. We have a lot of other observations. D just came down about an hour ago, and we don't have any observations of that yet. They will be coming in very soon. I think I'll give it back to you now, Gene.
Okay, thanks. Well, early this morning we heard from James Graham at the University of California reporting on fragments A and C from the Keck Observatory on Mauna Kea. And I think if we can roll now those observations, and we should have a direct audio report from Graham
Jupiter when the second impact was due. And we saw a distinct signature of the plume of one of the impacts. And then subsequent images show very bright features on the surface of Jupiter at the impact sites. They're incredibly bright, very clear. It's a very spectacular event. One of the things that has surprised us is just how bright these events are. And so the thing that the advantage the Keck has is that it can see much fainter things going on. And in particular, one of the experiments that we did this evening that will take some more time to analyze was looking at Jupiter's ring. And that has the advantages that by looking at reflected light off the ring, we can, in a sense, view the impact site directly. So hopefully when we look at that data carefully, we will see the initial flash when the comet fragment hit Jupiter.
Let's go on then. We have an image now from Fragment A impact from Cerro Tololo in La Serena, Chile. This is an image now coming up from John Spencer of Lowell Observatory, who's down at Cerro Tololo. And no, this doesn't look right.
The Graham image next.
Pardon
The
me?
Graham image is next.
We just had Graham.
There it is.
That's his image.
Oh, here's his image. Okay.
The image that you're looking at is a picture from the Keck telescope. It's an infrared picture at a wavelength of 3.3 microns, which is about 6 times the wavelength of visible light. The features that you see are the bright polar caps, which are always present. And just south of the equator is the storm system, and the red spot. But far south, about minus 40 degrees, are the most prominent features, which are the aftermath of the comet impacts that occurred earlier this evening. The brightest spot is the very first impact. The one on the left-hand edge is impact number C.
Fantastic.
Incredible.
Fantastic. I might just insert the comment there that it's very clear that these impact sites are going to remain visible. We've seen one now go through a complete rotation. We may see a whole string of these now by the end of the week, lighting up that latitude band on Jupiter.
String of pearls.
That's another string of pearls for Carolyn. Okay, now I think we should have the, coming up next on the screen, John Spencer's image from Cerro Tololo. And there it is. Again, John is going to give us a report tomorrow, so we'll have him on audio at that time. But I think you can see that we're getting good images now from many telescopes around the world. That's the impact site for A. We also heard from Glenn Orton at NASA's Infrared Telescope facility at Mauna Kea, who filed the report now that we're going to see, again on Fragment A.
Looked at how it was very clearly had produced a new cloud, which was quite long. When we observed the plume from C, it was clearly at the same latitude, but at first very difficult to distinguish from the cloud at A. And as the planet rotated and time passed, the plume from C became very much brighter, several times brighter than that cloud. The cloud from the A fragment turned out to be about the same brightness as the north and south polar caps. I'm very ecstatic about any of this. Witnessing this is kind of amazing. And what's amazing about both of these is the fact that B and C are both rather faint objects, certainly in the thermal infrared, in the near infrared. So F and G are known to be much bigger, much brighter, and therefore expect them to be. They're both much bigger objects than A, and so this is going to be a real show.
Okay, I guess we're going to see Glenn's actual images tomorrow, so we'll have an update there from Glenn Orton. I guess at this point we turn it back to you, Don.
Okay, then we'll turn it over to reporters here at the Goddard Space Flight Center for Q&A, and then we'll check with our other centers to see if we have questions there. Let's start here in the front. And please wait for the microphone and state your name and affiliation.
Bob Cook, Newsday. Have you had a chance to think about why it might be dark in terms of chemical terms or something like that?
I think we're going to wait to answer that question until we get some spectroscopy. We actually have been getting some reports of very interesting chemistry going on. Some of the telescopes in Hawaii have reported, I don't know how much detail I can go into at this point, but I think I'll leave it at saying that the chemistry appears to be very interesting.
That's a teaser.
That's a teaser.
Miles O'Brien with CNN. Let's talk, what about the significance of seeing those plumes for Fragment A? Not something you expected, just the significance of being able to see that, first of all, and then what you might think we might see on some of these potentially larger fragments.
You want to take that, Gene?
Well, Miles, I showed a theoretical prediction last night for the plumes, and as I look at the plumes that Heidi showed us now in that sequence, it looks to me as though the prediction is bang on. In terms of the timing, you get a plume growing up to a tall column, it cools at the top, and then it collapses and flattens and flows out and spreads out at the base. And I think you could see that whole sequence, and if I remember the times correctly that I saw in Heidi's images, we're looking at a time interval of about 8 or 9 minutes, isn't it?
18, 27 minus 18.
Yeah,
Nine minutes.
9 minutes.
From top to bottom.
And so we really expected the plume to start to collapse after about 5 minutes and flow out and spread, and I think that's exactly what you're seeing. And I think that's a beautiful testimony to the prediction that was made by Paul Hassig of Titan Research Corporation, who did that model. And what it also is saying is to get that size plume, we are in fact dealing with an object that had the energy of at least a kilometer-sized object, maybe even a little bit bigger there. So that means there's a lot of stuff even in these smaller fragments.
And the implication is that the later fragments will probably be even more extended and larger.
Yep.
Kathy? Oh, okay. We'll do a follow-up.
You've said earlier many times, Gene, that all your career you'd hope to witness something like this. You've studied craters, the residue of something like this. Now, having seen one, what are your thoughts?
Let me say, beyond the fact that we feel enormously relieved that there are really big objects there that are going to give us a show, it gives me a very warm feeling that we can in fact use some of the most sophisticated numerical models that have been developed with intensive effort over the last 3 decades and find that they really work on this enormous scale, and that we really can gain a close theoretical understanding of what is happening with each one of these impacts. I feel very good about that.
Kathy?
Kathy Sawyer, The Washington Post, for Gene. Can you tell me roughly what altitude you think the dark splotch is residing at currently, if it's fixed in a place, and what's there? What gases are at that level to the extent that you know, or could this be material that's been exposed from the interior, possibly?
The model calculations would indicate that the largest part of the material in that dark splotch actually consists of Jovian atmosphere that's been dredged up from beneath the ammonia cloud tops, but it will contain almost all of the cometary material as well. So there's, as Heidi said, there's got to be some wonderful chemistry going on. Remember, all of this stuff got very hot. We're talking about the initial fireball temperatures in the range of 30,000 degrees Kelvin, and then it cools off from there. And so there's some chemistry that I think we don't really know how to model. Just what those constituents are that make it dark and bright at the relative wavelengths is something that's still going to take a lot of work. The altitude at which you're seeing that reside later on, I think you got a hit from that, from the limb profile, but it's probably of the order, most of it will be of the order of a couple hundred kilometers, I think, above the ammonia cloud tops. Would you like to comment on that, Heidi?
I think that's where we're heading right now, too, mostly based on the methane band image, where we saw this material very bright. and similar brightness to the Great Red Spot, for example, if we could show the methane band image, which is the second graphic. By seeing this thing bright in the methane bands, and particularly in all the infrared images too, we know that it's got to be relatively high. I think we're going to have to wait for more detailed analysis before we can give a firm number on that.
Back here, third row.
Deborah Zabarenko, I work for Reuters. What can you tell us about what permanent effects this might have on Jupiter? These impacts seem to be brighter, bigger, you know, altogether more than you were predicting. And now that these look like they're going to be lasting features of the planet, how's it going to change? Is there anything you know at this point?
You want to try that?
Sure, I'll give it a whirl. Well, we won't know for a few days, I think, how long-lived these features are. It could be a very tenuous deposition of material, that splotch, and the zonal winds on Jupiter are pretty strong, so they could shear it out and spread it out. Based on what we've seen, however, just from the few that we've seen, it looks pretty clear that that whole band of latitude is going to be pockmarked with these impact sites. And heaven only knows what I'm going to show you a week from now when I show you that movie.
Yeah, except that we're not, at the moment, expecting that these impact sites and whatever is forming are going to last permanently. They're very brief. We're expecting that they will disappear within a matter of days or weeks,
Well,
right?
I don't think Bob West would agree with that.
Really?
No, we've got a program. We're going to
Really?
continue. Yeah, absolutely. We're dumping a lot of material in the stratosphere. And, you know, as we see in the Earth, when Pinatubo erupted and you threw all that material in the stratosphere of the Earth, it hung around for a long time. We were seeing beautiful sunsets for a very long time. So, you know, this stuff could hang around in the stratosphere of Jupiter for a while. And we have programs on the Hubble and many other ground-based telescopes to look for that for a week after, a month after, many months after. And we won't be able to tell you until we've done those observations how long it's going to hang around.
This may be one of the surprises we were looking for.
Yeah, I'm going to stop being conservative. Forget about all that. Caution to the
I think
wind.
maybe what you were leading to, Heidi, is that you know, as that higher altitude and stuff spreads out there, there's going to be a haze band, very likely, something that will be readily observable even with a small telescope on the ground. That may be a broad enough feature that it'll be seen for some time, which I think is exciting for everybody.
It'll be interesting to see if those features stay dark. That would be very interesting to see.
Senior Sky of NHK. Could you tell us a size of fragment B, C, D, E, and what happened to those fragments? I heard that the Hubble Space Telescope is taking a picture just 10 hours before the collision itself. So what happened to fragment itself before the collision? Is it broke down or it still keep the shape or something?
Well, I can try. It looked as though in the days preceding the impact of Fragment A, there was a report that the fragment was becoming much more oval, and one report said that the nucleus, it meant the nucleus was splitting up, but Hal Weaver definitely wanted to stop that idea, saying that it was just the dust coma around the nucleus that was starting to be pulled on by Jupiter's gravity so that it would start getting more elliptical. All the evidence we have right now indicates that Fragment A must have impacted pretty well intact. And that elongation we were seeing in the days before was simply the coma of that particular comet that was starting to get pulled in towards Jupiter.
But I think in partial answer, the thing that you were suggesting earlier, David, was that the nuclei that are off the line may in fact be essentially swarms of objects. So A may be mostly a single object, B may be a swarm, C is again mostly a single object, and we come back and we sort of pick out the candidates for just swarms. And those are the things that have less mass and less energy and will produce less of an effect when they hit Jupiter.
Up in front.
Glenda Chu, San Jose Mercury News. I have two questions. One for David Levy. The two reports that you got of flashes possibly being seen from small telescopes at Wise Observatory. Could you tell us where that observatory is and were those observatory, and how to spell it, and were those observatory telescopes, how big were they, or were they amateur telescopes nearby? And I have one other question.
Yeah, thanks. The WISE Observatory is in southern Israel. It's south of Beersheba, and it's in the Negev desert. Beautiful, beautiful conditions. Although I understand from Jim Scotty from the University of Arizona, who's actually observing there, that they have been having a lot of clouds, and we're really lucky that it cleared up at impact time or thereabouts. Surrounding the observatory that Jim Scotty was observing in were a whole crowd of either amateur or advanced amateurs or professionals with just small telescopes trying to see if they could see the flashes. Two people with, I believe, a 4-inch diameter and a 10-inch diameter telescope detected seeing the impact flashes. These are small telescopes that you can just go out and get in a store somewhere. And so I want to be very cautious about this, because no one else has seen this. No one else has reported impact flashes. However, it does mean that people with telescopes of that size, knowing exactly where to look on the limb of Jupiter, the edge of Jupiter, should be able to at least try to see if some of the later impacts will display meteor flashes as the initial meteor comes in.
The other question I had, I'm kind of confused about the term fireball that people keep using. As I understood it, there's no oxygen on Jupiter, there can't be any fire, and people keep talking about a fireball and a plume. What exactly, is this thing burning?
No.
Or is it simply very hot? What is it? Is it just an expanding bubble of hot gas, or can you describe it a little bit better?
There are a number of different events. The first we call the meteor phase. This happens when the fragment is coming into Jupiter, it enters Jupiter's stratosphere, it starts to interact with the atmosphere, just like a meteor on Earth that we see any night of the year. And next month, on August 11th, with the Perseid shower, we should be seeing a lot of them. But instead of a grain of sand producing the bright meteor, this is an object 1 kilometer that's well more than half a mile wide, producing a very, very bright meteor, lasting, like the meteors on Earth, a second or so. Then it disappears, it goes down into Jupiter's clouds, explodes somewhere well below the clouds, and then a huge fireball cloud comes up. We've all heard of the sad but accurate term, the nuclear fireball after an atomic explosion, where a big, huge cloud rumbles up and creates a plume that lasts for several minutes. That we call the fireball. And the plume, from that fireball, has apparently lasted a while, and then it collapsed just as Gene's model had suggested it would.
It's just a terminology that comes from nuclear experiments, where you simply created a tremendously hot atmospheric mass that's shocked. The heating is actually due to the shock, and the temperatures go up to temperatures that are way beyond anything in our normal experience on the Earth. The temperatures rise to tens of thousands of degrees Kelvin, and that's what we mean by the fireball. It doesn't mean that something is burning, it's just extraordinarily hot. The heat is coming from the shock wave, not from combustion. It's incandescent because it's so hot.
Bubble of hot gas is exactly the right way to think about it. Very, very hot gas.
Jim?
Jim Slade of ABC News. What do you have in radio emissions at this point? Do you have any seismic data?
I don't think that we've heard any reports of radio emissions at the present time. I'm certainly
From the impacts, there was that earlier one.
We heard a report from Japan. This came over the wire surfaces yesterday that predates the impacts, and we need to learn more about that. But in terms of radio emission at time of impact, I'm not aware that we received any reports in at the present time. The second question was?
Seismic.
Seismic. Well, you saw the seismic wave. There it is.
Where?
Right down there around your spot.
Not.
What do you think?
We were primarily expecting to see the seismic waves and the atmospheric waves in the infrared data more so than in the visible wavelength data. That's where you would directly detect the seismic waves. And in this visible wavelength data, you're seeing a secondary effect where the temperature causes some kind of cloud to condense in the atmosphere. From what I have heard and seen so far, we have seen the impact sites in the infrared, but I have not yet heard a report of seeing wave phenomena in the infrared.
Okay, now, Heidi,
Yes.
what's that ring around the dark spot?
Well, that's a good question.
I claim that's just about the distance at which the acoustic wave should have arrived.
Well, we'll know when we have another sequence of images where we can see that expand outwards. If we don't see that moving outwards, Gene, then it's not likely to be an atmospheric wave. This isn't the best one. We didn't expect to see anything. We didn't plan a sequence. We do have images later on where we're planning to take sequences over several orbits so we can see this wave move out. And certainly, as I said, in the infrared, that's where we really expect to see these seismic waves. If you see them here, you should see them in the infrared.
Yep.
Okay, so we're going to have to wait and see when we really look closely at the infrared data. You can believe anything you want at this point.
But you have to explain why that is out as far as it is, and I think that's just about the distance at which the acoustic wave would...
Well, okay, I'll go out on a limb here. I thought that that was debris that had fallen down. I mean, when we looked at that Plume image, it's very extended, and I thought that that circular pattern was the fallout from that plume.
Okay, we'll see. I'm betting it's the seismic wave. You're seeing an effect in the atmosphere due to the acoustic wave.
We'll see.
Okay.
This is Mark Kuro of the Houston Chronicle. Could you go over which of the fragments you think are the largest and some estimate of what size you think they might be? And as a related question, the impact information you're getting now, what is it telling you about what these fragments are actually made of?
What? Well, let's look at the panel in the back. This is a wonderful. There it is. Here's the graphics coming up again. Only they've got those horrible numbers. I think in A, B, C, and D. No, they're all numbers.
Except for A.
Except for A.
Except for A. All right. Number 24 on there, which is G, that big guy behind us.
That's tomorrow.
G and H are the biggies. Let's see, what else is in here?
That's I.
Gene, they have it with
There we go. All right, now we've got it. H and K are all goodies. L is a little bit smaller. Q1 is another biggie. Those are the real big ones. And if we can gauge now from nucleus A and the effects we got from that, then I would say Hal Weaver's estimates of the sizes that came out now and were published in January are probably very good. And so we're talking about probably 3 kilometer size objects for G, H, K, and Q, Q1.
Dick Kerr, Science Magazine. In the Graham images, we saw 2 spots. Those were A and C. Did B fail to create one of those spots, or was it just not in that view? And what would that imply about mass or the nature of that object?
Well, B would have been on the other side.
Yeah.
B would have been out of view, I think, but B was detected at Keck.
At Keck.
One more question here, and then we'll go to Kennedy Space Center and come back after that.
Bob Hager with NBC. Did the new observations tell you any more about the amount of energy released during this event with A and the amounts that you could expect down the line as the others hit?
Well, what we can say is that from what we saw on A, it was much more energetic than we expected. And so the kind of energetics we were expecting were 10 to the 29 ergs, 100 million megatons for G. So it seems like we're seeing that kind of energy for A. It seems to be more powerful than we expected.
100 million megatons for A.
No, I'd say about.
You know,
I think we're off by a factor of 10 there.
Are we?
Yeah.
10 million megatons.
Yeah.
All right, I'd like to go to Kennedy Space Center. We have some questions there. We will check the other centers and come back here. Go ahead, Kennedy.
Phil Long, the Miami Herald. Two questions, rather non-technical, and they sort of come from what Heidi said about the possibility or the good thing that it's going to Jupiter. A lot of people are wondering today kind of a what-if question. So what effect would it have had if this had come down anywhere around North America? And the second question is, a lot of people don't understand an object of this relatively small size, how it does such massive damage.
Okay.
You want to do that one?
Well, if A had hit North America, it's likely, first of all, it would have made a crater about 20 kilometers in diameter. Of course, if that happened over the Baltimore, Washington area, it would have taken us all out. We wouldn't be here. So the local damage would have been just enormous. You not only take out what's in the crater, but you take out everything that's in the ejecta blanket of the crater, and you knock down things for hundreds of kilometers or hundreds of miles beyond that. But also then a tremendous amount of polarized material would have been carried up into the high atmosphere and ultimately would spread over all of the northern hemisphere. You'd probably get a very significant global climatic effect from that single fragment. So it would be a major disaster. It would be probably the worst natural disaster ever witnessed by man.
And that's just for a single,
one.
Tiny first fragment that we didn't expect anything from.
And the second part of the question, how does such a relatively small object cause that much disturbance?
Okay, the thing to remember is that any mass of material, doesn't matter whether it's lead or custard pie, if you take 1 gram of that material and move it at the speed of 3 kilometers per second, that's getting pretty fast. That's faster than a very high-powered rifle bullet. Its kinetic energy is equivalent to the same to the combustion of the same mass of high explosive, like TNT. Now the energy goes up as the square of the velocity. So for each gram of that comet coming in, we'll have not just the equivalent mass of combustion of a gram of TNT, it will have 20 squared times as much. In other words, 400 times as much energy packed into each gram as the energy of combustion of TNT. That's why it's so damaging.
This is Todd Halverson of Florida Today. We've heard you all talking about Fragment A. I'm wondering whether or not at this time you can describe what was seen with Fragments B and C. And I realize D was just happening, I guess, right before you came on the air here.
C was observed as strongly as A was. And more recently, we don't have as much analysis from C as we did from A. B was seemed to be a lot weaker, and so far we're interpreting that as being that B is probably composed of more of a rubble pile. By the rubble pile, it was just a loosely congealed group of very tiny fragments, and as it got closer to Jupiter, just before impact, they just kind of fell apart. And what probably happened is that most of B exploded much higher up in Jupiter's stratosphere. Probably little of it, or not as much as we thought, got down into the atmosphere. However, the Keck telescope, which is now the world's largest ground-based telescope, did observe an explosive plume from B. This is something that we thought we'd be lucky to get on any, remember when we were upset earlier that these impacts are going to be on the night side, we're not going to see anything from Earth? Even with weakly put together Fragment B, we're still seeing the explosive plume from Earth with ground-based telescopes. C, on the other hand, appears to have been more of a solid fragment, came right down like A did, and made a much larger explosion. This is just our tentative idea, but most of us seem to agree with that.
At this time, just a quick follow, at this time, can you give us an idea of how high above the limb the B and C plumes travel?
We can only speculate that for A at this point because that's the one we have the highest resolution imaging, and we seem to believe that the bright detached portion of that plume was about 1,000 kilometers above the limb of Jupiter.
And I'm wondering if you could just review quickly for me the impacts that you anticipate the rest of today and tomorrow.
Okay, I can give you a rundown on that. In Eastern Daylight Time, Fragment E is coming down at 11:05, so not very far away. Fragment F will be at 20:27 Zulu time. Of course, that's 8:27 this evening. And then Fragment G will come down tomorrow morning at 3:29.
Okay, so 8:27 this evening, Eastern, is that
Eastern Daylight Time. Eastern Daylight Time.
So observers with small telescopes should be trying to watch at the right spot on the limb for brief flashes. Be really careful, though. I'm not saying that Jupiter is going to get millions of times brighter. This is going to be something that if you really know what you're looking for, there is a chance that you might detect the flash.
I want to qualify that to say that there have been no reports from any professional observatories detecting those flashes.
Yes.
And they've been looking, so.
And I would add to that we went to the U.S. Naval Observatory last night to put our eye to the telescope in hopes of seeing a flash. And when you really want to see a flash, you can almost imagine that you do. So we all have to be careful that we aren't imagining something that isn't quite there.
Yeah, very true. And we've always tried to explain those two tentative reports. They have to be mentioned because they were reported by more than one observer, but it is something that has not, I don't consider that it's been confirmed. The only way to confirm something like that is to increase the number of people trying to observe them.
Mm-hmm. Timing would be all important. The one thing to remember, however, is a visual observer has the advantage of being there and watching all the time, and you may not capture that very brief event, which will last only 2 or at the most 3 seconds if you're not taking the image at the right time. So there are some advantages the visual observer has. The disadvantage is it's hard to prove that you saw it.
More questions from Kennedy?
Yeah, one other quick follow from me. Are there other anticipated impacts tomorrow besides G, or in addition to G?
Oh, sure.
Let me say that we have that information available, and that should be at the newsroom at Kennedy, and if it's not there, we will fax a full list of all the impact times and locations where those can be viewed from, and the observatories that are likely to have an opportunity to observe those, as well as the Hubble observing schedule. So that should be in the newsroom at the end of this briefing, if it's not already there. Any more questions from Kennedy?
Yes, two more reporters. This is Phil Chen, Earth News for Heidi. I'll make it easy on your video person to tell them that I need you to display the graphic showing your little movie of the fireball coming in. It's got 2 vertical scales, one of time and one of wavelength. What happens when you stay at one wavelength? Do you still see the same expanding, or alternately, what happens if you stay at one time? How different does it look in the different wavelengths?
Well, the data you saw are the data we have. We only took that data because we were sampling at various wavelengths. So I can't answer that question. Not yet. I think that if these things are visible at this level, and particularly for the brighter fragments, that some of the other ground-based observatories will be able to do that experiment. We're not really particularly designed to do this kind of an experiment with the Hubble Space Telescope. By this kind of experiment, I mean something that has very rapid time sequence. That really wasn't the point of this. This was purely serendipitous that we did see it in a time sequence like that. So I think you'll have to wait and hear from the ground-based telescopes that are designed to do that kind of an experiment.
Okay, on the other side of the spectrum, in the infrared, have you heard any reports from the McDonald Observatory or from the Kuiper Airborne Observatory, which I believe is flying out of Australia?
We haven't gotten a report yet from the Kuiper Airborne Observatory. Observations were scheduled, so I hope maybe we'll be able to report on that tomorrow.
We're attempting to contact them throughout the morning to get what we can and post that as soon as we could.
Okay, and Gene, a really big picture question. A couple of us here and on the panel were in elementary school at the time, but were you more excited 25 years ago preparing for Apollo 11 than you were now for this, or more excited now?
That's kind of hard to compare. They're different events. I think that we all had a lot of confidence in Apollo 11 that it was going to be a successful landing. So when it happened, we said, all right, it happened, and we were all delighted and grateful for that achievement. What's different with this situation is we didn't know how nature was going to perform. And we're just elated that nature has outdone herself to give us this spectacular experiment that we're looking at now.
Phil Long, Miami Herald again. Just one more quick question about the spots themselves. To the layperson, there might be some confusion. It's described as a dark spot or a light spot. That may be just simply the technology that observes it. But to someone who is going, say, to the local community college observatory, what should they look for? What could they expect to see? And could you explain a little bit why it appears light to one and dark to the other?
Yeah, I still doubt that people with small telescopes are going to be able to detect these features at all. I doubt very, very much. They're looking awfully nice, but remember, these pictures are with very large ground-based telescopes or with the Hubble Space Telescope. I strongly suggest that people go to their local observatories, planetaria, and look at Jupiter. And I still think that you will probably see no changes on Jupiter. I will be thrilled and delighted if I'm wrong on that. But go out with your telescope, look at Jupiter. Don't expect to see more than the beautiful Jupiter it always is. And then keep posted to HST and the other ground-based telescopes to see the real changes that we are seeing. And if I'm wrong on that, then I'll be just as thrilled as anybody else.
To answer the question more directly, at visible wavelengths, if you were looking with your eyes, if you were out at Jupiter, you would see dark spots. In the visible, these features right now are dark. When they're fresh, they're dark. The only time that they're bright is when we're looking in the infrared, and that's because these features are hot. When they're hot, they're bright in the infrared. So we have something that's visually dark and hot. So it's dark in the visible and bright in the infrared. And the methane band is bright because the methane molecule is absorbing all the other photons except the ones that are getting reflected off of these particles. Does that help clarify?
All right. We'll go to JPL now for a question, and we'll be back here for follow-ups. Go ahead, JPL.
This is Robert Lee Host with the Los Angeles Times. Just a simple fact question. If Fragment A, your best guess is that it's about a half mile wide, then what's your best guess on the literal size of B, C, and D?
I'd say Fragment C is very comparable to Fragment A. They're very, very close. So we're talking about something of order of a kilometer, 0.6 of a mile, something like that. These are rough numbers, please remember. As far as B, it's much harder to say. It clearly produced much less effect, so the total mass is less, and it may have been a loose swarm by the time it hit the atmosphere, not a single object. So it's a little bit hard to put size on that. If you wadded it all up together, perhaps it was something that was of the order of a few hundred meters across, I would guess. You want to take a shot at that, Heidi? Do you have a...
No, I think you did a great job.
Okay.
We got the letters on the fragments now.
Oh, good. Now we got the
wonderful.
Okay, we'll come back here to Goddard and take some questions. Have one up in front here.
With Galileo on the way out there carrying a probe to drop into this very same atmosphere, how do you think these results are going to inform what people are looking for when that happens?
You want to try it?
I can try. We're going to be thinking very, very carefully about what we see. And Galileo is actually taking pictures of these events. So that'll be fascinating to see what the Galileo spacecraft sends back, because they had direct views of these impact sites. Certainly, the changes in the Jovian atmosphere are going to be very interesting. And I think it's great timing that NASA has a spacecraft on its way to Jupiter right now, and we'll get there and see these things up close.
The other thing is that the Galileo probe, the probe part of it, was very carefully designed to go down into a certain depth below Jupiter's cloud tops. One probe, an active probe with instruments. We now have 21 small passive probes going down all the different layers of Jupiter's atmosphere and revealing whatever they can reveal. Each one of these comet impacts is a little bit like a probe going down, very much like a probe, going down below the cloud tops, sending up stuff from the interior, telling us an enormous amount of what Jupiter's made of and what it's like. We need to look at these things as being almost like probes.
Next question.
Mike Nickerson, NHK. Yesterday we learned that there was a 13-minute deviation from the predicted time of the impact of A. And do we have specific impact times and same sort of deviations regarding B, C, and I guess D now?
Heidi, you've got the first timing that shows the plume coming up. And it was at 2018, which was exactly the time given by the people at Cala Alto in Spain. So the impact probably is a little bit before that, by as much as perhaps 3 to 5 minutes. I would guess that that's the offset.
I haven't heard any reports of accurate timing of the other ones yet. So I don't think we know the answer to that question as to whether the whole chain is offset by that amount. We'll be working on that throughout the day today to find that information out.
If we can get reports of direct radio signals, for example, from Ulysses, that would probably give us, that might give us the most precise timing, because that Ulysses can look directly at the impact site at short radio wavelengths, and we might see that plume should produce or even the meteor may produce a radio signal that would give us the exact impact time.
Okay. Also, I wanted to ask you about some of the other phenomena that had been predicted, such as an aurora effect and or reflections off some of the Jovian satellites. Have any of those been observed?
No observations that we've gotten yet of reflections off the satellites. That's interesting that we haven't gotten that, and yet we've gotten so many positive things in other areas.
However, those are hard to observe when the satellites are in sunlight. Wait for Fragment K. When Fragment K is going to impact, Europa will be in the shadow of Jupiter, and that will be a very sensitive test then. And the initial, we should see the flash of the initial entry meteor there. We may be able to get that directly from observations of Europa at that time.
And I believe we're getting some ultraviolet images with the Hubble today, and those will be very interesting for studying the aurora. Hopefully John Clark will be able to talk about that tomorrow or perhaps the next day.
Bob.
What is it that the comet fragment encounters from the time it enters the atmosphere down to the point where it explodes, and what is it that causes it to explode?
Okay, the comet is entering the very tenuous uppermost part of the Jovian atmosphere initially, and it simply increases a denser and denser atmosphere as it goes down. By the time it hits the ammonia cloud tops, it's reached the half bar level. In other words, a pressure about equal to half the pressure in this room. But it continues for these larger fragments. Theory predicted if they are single fragments, it'll punch right on down and go to the depths of order about several tens of kilometers below the ammonia cloud tops. At some point, for a given size fragment, what will happen is the comet is being decelerated by the intense shock, the bow shock ahead of it. and it simply becomes crushed by its own inertia, because of that deceleration by the shock wave. And when it crushes, it just falls apart. It just spreads out and falls apart, and that then presents a very broad area, which again now is going to stop it very quickly. In other words, it meets much more atmospheric resistance and is stopped very suddenly. So that essentially all of the kinetic energy that was in the comet fragment to begin with is delivered to that shock wave. And a little bit of course, remains in the comet, which itself gets heated to tens of thousands of degrees Kelvin as well. So it's basically just transferring that initial kinetic energy into a shock wave, and most of it, but not all, ends up at the lower part where the comet essentially just comes apart rather suddenly.
Is it still in ammonia clouds at that point?
It's below them. We think it's below them. Well, remember, it's still mostly hydrogen. The ammonia clouds are just a portion of the atmosphere, but the atmosphere is mainly hydrogen all the way down.
Heidi, are we apt to see HST images of the impact of E today? I know there's nothing officially scheduled, but yesterday there was sort of an early release, and I'm wondering if there's some excitement about what you see. They might be released sooner than expected.
I don't really know the answer to that. I think we're not getting our images downloaded until later in the afternoon. They're not coming down from the spacecraft. And so we may just have to wait till tomorrow morning.
This is Mark Kura of the Houston Chronicle. Could you, I know the question's rather basic, but I'm still not sure I understand what you've learned about what the fragments are made of, and in a general sense, kind of how they're, if they're multiple pieces, how they're grouped together and interacting with each other. Has anything that you've seen from the impacts helped clarify that?
Well, only the one thing is that when you have pieces that appear to be the same size in our Hubble Space Telescope January photograph, and A and C come down really, really strong, and then B is really weak, the implication is that B is really loosely held together.
What is it that the comet fragment encounters from the time it enters the atmosphere down to the point where it explodes, and what is it that causes it to explode?
Okay, the comet is entering the very tenuous uppermost part of the Jovian atmosphere initially, and it simply increases a denser and denser atmosphere as it goes down. By the time it hits the ammonia cloud tops, it's reached the half-bar level. In other words, a pressure about equal to half the pressure in this room. But it continues for these larger fragments. Theory predicted if they are single fragments, it'll punch right on down and go to the depths of order about several tens of kilometers below the ammonia cloud tops. At some point, for a given size fragment, what will happen is the comet is being decelerated by the intense shock, the bow shock ahead of it. And it simply becomes crushed by its own inertia, because of that deceleration by the shock wave. And when it crushes, it just falls apart. It just spreads out and falls apart, and that then presents a very broad area, which again now is going to stop it very quickly. In other words, it meets much more atmospheric resistance and is stopped very suddenly. So that essentially all of the kinetic energy that was in the comet fragment to begin with is delivered to that shock wave. And a little bit of course, remains in the comet, which itself gets heated to tens of thousands of degrees Kelvin as well. So it's basically just transferring that initial kinetic energy into a shock wave, and most of it, but not all, ends up at the lower part where the comet essentially just comes apart rather suddenly.
Is it still in ammonia clouds at that point?
It's below them. We think it's below them. Well, remember, it's still mostly hydrogen. The ammonia clouds are just a portion of the atmosphere, but the atmosphere is mainly hydrogen all the way down.
Heidi, are we apt to see HST images of the impact of E today? I know there's nothing officially scheduled, but yesterday there was sort of an early release, and I'm wondering if there's some excitement about what you see. They might be released sooner than expected.
I don't really know the answer to that. I think we're not getting our images downloaded until later in the afternoon. They're not coming down from the spacecraft. And so we may just have to wait till tomorrow morning.
This is Mark Crow of the Houston Chronicle. Could you, I know the question's rather basic, but I'm still not sure I understand what you've learned about what the fragments are made of, and in a general sense, kind of how they're, if they're multiple pieces, how they're grouped together and interacting with each other. Has anything that you've seen from the impacts helped clarify that?
Well, only the one thing is that when you have pieces that appear to be the same size in our Hubble Space Telescope January photograph, and A and C come down really, really strong, and then B is really weak, the implication is that B is really loosely held together and wants to just come apart as soon as it starts interacting with Jupiter's atmosphere. Other than that,
Spectroscopy.
Spectroscopy does it.
We'll wait until we get some spectroscopic results from some of the ground-based telescopes and the Hubble Space Telescope, and that will give us information about composition of the material that we're seeing, and whether it's Jovian dredged up from below, whether it's cometary spilled in, or whether it's some incredible mixture of the two is going to take a while to sort out. But that's one place where we will get some interesting information about the comet's composition.
So you'll be doing a chemical analysis, I gather, but is this dust, ice, rocks, is that still what you think's there? I mean, that's what I'm not clear on.
Yeah.
The prevailing party line on comets is it's a mixture of ice and silicate rocky particles, and now we know from the observations of Halley's Comet that there's a fair amount of very complex organic material that are called Chon grains. They're composed of carbon, hydrogen, oxygen, and nitrogen. It's kind of a tarry gunk, if you want to think of it that way. That was a substantial fraction of the dust that was coming off of Halley. All of that's mixed together in some kind of a mud ball, if you want to think of it that way, an icy mud ball. Whether it's solid or whether it's porous and fluffy, those are all $64 questions. There's a wide variety of opinion about that, and I don't think that we can really say yet from what we're seeing with these impacts. We can't shed much light on it. I have a personal prejudice that these things are not all that porous. That is to say, the pore space might be a few tens of percent, but the density of the object is more or less like the density of a ball of ice.
We have time for just a couple of more questions before we'll lose the satellite today, and we would like to replay all the images, stills, video, and animation that we had available today while we still have the satellite. So we will go a couple more questions. Of course, the people here in the room will still have an opportunity to ask a few more following that, but we'll take another second row.
Matt Crenson, the Dallas Morning News. G is 25 times more massive than A and C. Do you expect that that extra energy will bump you up into a different kind of scenario from the fireball one that you've been describing, or is it just going to be a bigger boom?
I think we're getting basically the same phenomenon, but a much bigger boom. Now, there is the possibility that some of these much larger objects, if they remain intact, can go very much deeper into the Jovian atmosphere. And so there is the possibility that that boom may be muffled, that not as good an eruptive plume will come back out. So that'll be very interesting to watch and see, but we're certainly delivering that much more energy to the planet.
A better chance for some of these wave phenomena, whether it's an atmospheric wave or the seismic waves that Gene is sure he sees already. Much more likely that for a large body that those effects will be visible.
Question in the third row.
Michael Chuchek, TV Asahi. This is a question for Carolyn Shoemaker and for David Levy. This Shoemaker-Levy 9 was discovered in what is essentially very old technology, and now it's being observed with the latest and most expensive of technology. I'd like to hear your comments about the way science can be done and the way it has been done here.
I think that scientists tend to use whatever is available for the funds that they have. I think very good technology can come out of older methods. The telescope that we use at Palomar Observatory is ideal for that purpose, for the search of small bodies in the solar system, because we can cover such a wide area of the sky. You could not use one of the beautiful big new telescopes that can look very deep and cover a lot of sky. But I think that we're very fortunate today to have the advantage of all the new technology, because once you find something, then you want to look a lot deeper. If we didn't have the wonderful telescopes that exist today and the new technology, we wouldn't begin to know what this comet is really like and what it's doing.
It's really important and valuable to be continually developing new technology. One of the things that we always love when we're at Palomar is to watch ourselves observing with Palomar's first telescope, built in 1936, designed essentially by amateur astronomer Russell Porter, and still in use, a telescope that has made more comet and supernova discoveries than any other telescope in the world. And it's important to have the new technology that is necessary now. Without all the new technology, we wouldn't be nearly as excited today. We wouldn't be excited at all today as we are. But I think it's also important not to toss out the old technology too fast. We're seeing how valuable that was in at least bringing this comet to everybody's attention.
We have time for about one more question before we lose the satellite. Anyone? Glenda, front row.
David, you said you were a little bit surprised by the idea that people would be able to see some flashes, especially from a big object, that these usually flashes would come from smaller meteors. But I wonder if it's possible, aren't these comet fragments traveling along with a lot of other little bitty things that we can't really see? And I wonder if it's possible, if these people saw something, that they were actually much smaller little bits traveling along with the main fragments that might have produced flashes.
That's a good, intriguing question. I don't think so. I think a small fragment, the only way that a small fragment could give a brighter flash is if it exploded so much higher in Jupiter's stratosphere that it was simply visible from the Earth, because it was simply so much higher. The smaller the fragment is, the higher up in Jupiter's atmosphere is likely to explode. My guess is, if these visual observations are correct, and that is a huge if they're confirmed, then my guess is that they were the main impacting fragment of A. But can't be sure based on that limited data set.
Okay, we're going to hold other questions for now. What we would like to do is give the cameramen and TV crews an opportunity to reset up for a replay of the images and video animation coming across in just a couple of minutes, if you need that kind of time to set up. If you're ready to go, just give a sign and we'll roll the tape whenever you're ready. And while you're setting up on that, I just want to make an announcement about our briefing tomorrow to remind everyone. The Comet update tomorrow will, we hope, have information on E, F, and we may conceivably have some sort of information on G, but I understand that's pushing it for Hubble information that's very close to the time that the impact will have occurred, so we may only just know that it happened. But whatever we have at that time, of course, we will make available as soon as we can. Other observations from IRTF and from Kuiper and other observatories, of course, we'll try to get that information and put it out as soon as we can, and have a briefing on that tomorrow morning here at Goddard at 8 a.m. Eastern Time. And please stay tuned also to us for any possible time changes or briefing changes throughout the week if we have an opportunity to include a report that's more inclusive or has some better images. We may, in fact, go to a later time in the day if that's necessary. We'll put out the word, and please check with us, and we will let everyone know. And I think we're ready to roll the video. And at that point, I'd like to thank everyone for coming today, and we will see you tomorrow morning. And thank you, panelists.
When the second impact was due, and we saw a distinct signature of the plume of after one of the impacts, and then subsequent images show very bright features on the surface of Jupiter at the impact sites. They're incredibly bright, very clear. It's a very spectacular event. One of the things that has surprised us is just how bright these events are. And so the thing that the advantage the Keck has is that it can see much fainter things going on. And in particular, one of the experiments that we did this evening that will take some more time to analyze was looking at Jupiter's ring. And that has the advantages that by looking at reflected light off the ring, we can, in a sense, view the impact site directly. So hopefully when we look at that data carefully, we will see the initial flash when the comet fragment hit Jupiter. The image that you're looking at is a picture from the Keck telescope. It's an infrared picture at a wavelength of 3.3 microns, which is about 6 times the wavelength of visible light. The features that you see are the bright polar caps, which are always present, and just south of the equator is the storm system and the red spot. But far south, about minus 40 degrees, are the most prominent features, which are the aftermath of the comet impacts that occurred earlier this evening. The brightest spot is the very first impact. The one on the left-hand edge is impact number C.
How it was very clearly had produced a new cloud, which was quite long. When we observed the plume from C, it was clearly at the same latitude, but at first very difficult to distinguish from the cloud of A. And as the planet rotated and time passed, the plume from C became very much brighter, several times brighter than that cloud. the cloud from the A fragment turned out to be about the same brightness as the north and south polar caps. I'm very ecstatic about any of this. Witnessing this is kind of amazing. And what's amazing about both of these is the fact that B and C are both rather faint objects, certainly in the thermal in the near infrared. So F and G are known to be much bigger, much brighter, and therefore I expect them to be, they're both much bigger objects than A, and so this is going to be a real show.
So it's on the way on the other side. Okay, we're looking for something. Why don't you undo that? This is the first one. Yeah, this is the latitude that we're looking for something right there. Contours you could tell pretty well, but there wasn't too much there. This is the 4-second thing.
So there's a red spot. Atlas is
Oh,
yeah, that's it.
my God.
That's it.
Look at that. Look at Look at 953.
Unbelievable.
Gotta get to the internet.
That's the way to do it.